Now, folks, I have a new toy. A couple weeks ago at a math department meeting, one of the instructors said, I'm going to send you information on a Wacom. Now, I've used Wacom screens and things like that before. In fact, my last computer, the one that died in spring term twice, had a Wacom built into it. You know, it was a tablet PC, so you could write. Well, the instructor that was talking with gave us the information. My wife ordered this, and we got it installed over the weekend. It came in last week. We got it installed over the weekend, and it seems to do okay. It's a lot better than my right finger on writing on the whiteboard. It's still not perfect because it has some idiosyncrasies, and I can use my left hand, but you see, I sort of write like this. If you've ever noticed left-handed people, they do, meaning I drag my hand across the top of the page. Well, if you drag your hand along the top of the page with this Wacom, you press buttons you don't want to press, and things will pop up that you don't want. They usually, so far, have faded out. So you'll see me and hear me fuss about it some. And then there are other things about this I don't understand yet. Sometimes it just sends a mark across the page that I don't know if I did something or it did or what. Other times it will skip when I'm trying to write, and other times it'll write more than what I intend to write. A lot like my finger was on the whiteboard. So we've still got some problems like this, but it's much easier writing on my part. I'm still learning to use it, still getting used to it, but so bear with me. If you think it's not as good as what we were doing before, I'll go back to the previous. All right. Now, both of you were here last time, so I think you recall we are in Chapter 3, Determinants, 3.1, the determinant of a matrix. And we had just done the technical definition for the determinant of a matrix. And I just as soon not write that again, except the first thing where we left off last time was confirm that for a 2x2 matrix, the definition holds. So I think I have to write that. And I want to show off my new toy anyway. So I'm going to do it, except I was just rubbing my finger on the Wacom. That doesn't work. I need to be on the keypad. And there we go. So I'm going to go to screen share. Anything else before we start screen share? Nothing? Okay. Whoops, here's Manuel. So let me let him in. I knew there was a reason we were waiting. We wanted Manuel to get here. Now, I think y'all recall, because I can't remember if she said it in this class or the previous class. Ricky is in both morning and midday class on Tuesday and Thursday. She shared it in one class. I don't remember if it was this one. Let me give you sort of the whole picture here. Her grandfather had been sick and in the hospital. Nothing to do with COVID, okay? But he had been sick and in the hospital, and her mother was taking care of him, and her dad was helping with that too, okay? In fact, I think that the grandfather had come home from the hospital, and her dad had been over there helping him get established back at home. I may have the story a little off, but something like that. And then within a day or two of having done that, helping this guy who had just gotten out of the hospital for some other condition to get established back home, older guy too, the dad started having symptoms and ultimately tested positive for COVID. So her dad has COVID now. Well, then the bad news was, if that's not bad enough, the granddad, home from the hospital recovering from whatever that was, he started showing symptoms as well and came down with pneumonia. She actually said he came down with pneumonia. So I think they sent him back to the hospital. I don't know if they've tested him yet and if they've confirmed, but the odds are he probably got COVID from the father when the father didn't know he had it, and you know, it was asymptomatic. More than likely that happened. So now the mom's taking care of the granddad, either at the hospital or at his home, wherever he is now, and Ricky's having to take care of her dad. So that's a really tough situation. She has to be quarantined until her dad gets over, and she goes for 14 days with, so her dad shows that he's over it, and she has to go 14 days after that so she didn't contract it. But, I mean, she's still trying to keep up with class, but when she's having to take care of him, she can't be in class. So she's trying to do it by the Screencast-O-Matic, and that's why I want to make sure I'm recording. And she's keeping up with homework and things like that as well. Okay, so that's why you may not see her in class as much as we used to. All right, so let's go to the whiteboard, which is where we live in this class, okay? All right, here it is. Now I'm going to move some things around. I don't think you see them, but I sure see them, and they're in my way. So the first thing I'll move is the taskbar for the Zoom, and then I'm going to move the taskbar for the whiteboard. Y'all probably can't see either one of them. And then I'm actually going to move the whiteboard so I can take advantage of more of the white space on it, because the block with your names on it are taking up over, and I'm going to actually move that block a little bit because, you know, James is just always in the way. Okay, so there, we got it. All right. So what I'm going to do now on my new toy, and you see if you like it better or worse than before, here was the definition of the determinant of a square matrix. Now that's almost redundant. To take a determinant of a matrix, the matrix has to be, without a doubt, square. You cannot take the determinant of a rectangular matrix that is not square. Okay, so we've got a square matrix, and here's what its determinant is. Okay, there's my pen on my Wacom. So the determinant of A is equal to the summation from j equal 1 to n, and this is where some things get squirrely. That equal sign, the first bar showed up, the second one didn't. From 1 to n of a sub ij c sub ij. Can anyone remember what the c sub ij stood for? I'm sorry, I'm writing that wrong. Go over here to my eraser. These are ones here, not i's. They're hard to see in the book. Okay. Go back to my draw tool. Okay. A sub 1j, c sub 1j. Okay. Which, by the way, turns out to be, now the first subscript for both the A and the C are 1s. So that's A 1, and then the first one for J is a 1. Okay, A11, capital C11. No one answered my question. What does that capital C stands for? Plus, say again? Cofactor is what you said? Okay, for some reason it's coming in pretty faint, but I heard you. Okay. A1, C11 plus A, and the first is always a 1. Now it's a 2 because you're counting up by 1. That's supposed to be a C, 1, 2, plus A13. There my hand landed on that thing, pressed a button. That's supposed to be a 1, 3, C13, plus dot, 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 all the way up to, and see those two dots connected, they shouldn't have, the last one would be a plus A sub 1n C sub 1n. Okay, that's your technical definition of how you do the determinant of a matrix. Now, what they've done here was use the first row. Now I'm moving my finger on my Wacom and that doesn't work. We use the first row because we used I equal 1. We used the first row and then went down the first row, taking the entries off the first row, multiplying them by the cofactors of that entry on the other rows, and did it all the way down till you got to the nth row, and it was an n by n matrix, so you stop there. Okay, we did this last time. Now, what they're asking us here is to confirm that when the 2 by 2 matrix that this holds. Okay, well, we know what the determinant of a 2 by 2 matrix is, and that would be determinant of a 2 by 2 would then be, we know what that is. And see, again, that minus sign doesn't, the equal sign doesn't do well. Okay, that would be A11 A22 minus A12 A21, right? When you do the cross product, first you go down the diagonal, that's A11 times A22, positive, and then you go up the other diagonal, minus A11 A21. Well, time out just a moment. What is the cofactor of A11? Cofactor of A11, C11 for a 2 by 2, wipe out the first row, first column, it's C11, okay? That's it right there. That's A22. Then minus, well, wait, this is a plus up here, A12 times the cofactor of C12. Well, A12, there we've got the A12 in there, okay? But where's the minus sign comes from? Well, the 1, 2 position is odd. 1 plus 2 is 3, so that gives you a minus sign there. And if you wipe out the first row, second column, A21 is the cofactor of that. So that's, sure enough, that is the right formula. That's what we've been using before. It is correct. Okay? Now, when you use this definition to evaluate a determinant, you call it expanding by cofactors in the first row. Okay? That formula up here at the top, that is expanding by cofactors in the first row. Okay? In order to do example 3, I think what I'll do is erase what we've got here, even though it might be fun to keep it. I'm afraid we'll need more room. We usually do. So let me clear. I keep using my finger when I've got the pad here, and let me clear the drawings here. Okay, so here is matrix A. There it is. A is equal to, okay, do you find this better than writing with my finger? Let me know. 0, 2, 1, because I'm able to use my left hand. 3, negative 1, 2, and 4, 0, 1. What do you think? Do you prefer my finger or you prefer the stylus and the Wacom? Okay, I thought so. I prefer it too, big time. Okay, so how do we do the determinant of A then? Okay, now we're going to use the first row. And by the way, that's not a bad choice at all. Here's the first row. There's the first row right here. And it's not a bad choice at all. And what that formula said to do, now I'm going to do the determinant of this, which is going to be the determinant of this. what they told us to do was start with the entry A11. That's a 0. But since this is our first time doing it, I'll write it down. That would be 0 times the cofactor of that entry. You wipe out the first row and the first column, right? And you do the determinant of this minor. And it's the positive determinant because 1 and 1 is 2, and that's an even number. So it is 0 times the determinant of -1, 2, 0, 1. That's the minor 1, 1, and the cofactor is the positive sign of that. So that's what we've got. Okay, continue down the first row, and this is how I do it. I go on and determine what the sign of that cofactor is. And what is the sign of this entry right here? This is a 1, 2 entry, so what will its sign be? Not the sign of the final answer, but the sign of the cofactor of that entry right there. Minus, exactly, plus minus, okay? So therefore, I'll go on and write in the minus 2, because that is the entry, then times the minor. See, if you take care of the sign first, you've gotten rid of the cofactor part, and now all you deal with is the minor. And the minor of the 1, 2 entry, you would wipe out the first row and the second column, and the matrix you have left over is 3, 2, 4, 1. So 3, 2, 4, 1. Am I skipping too many steps doing it this way? Okay. Then what you do is go to the 1, 3 entry, because you're using this first row to calculate your determinant. Well, what's the sign of the cofactor of the 1, 3 entry? Positive, so I'm going to put a plus there. Okay, I've got to get used to this plus. It's sort of wiggling all over the field here. And the entry is 1, okay? And then what's the minor for that entry? You wipe out the first row here, the third column here, and the minor is 3, -1, 4, 0. Okay, so it's times the determinant of 3, -1, 4, 0. Okay, now let's go back here. Certainly 0 times whatever that determinant is going to be 0. So then you move to here and you get a -2 times the determinant here. And can someone do that fairly quickly? Okay, you get a 3 here, -5, perfect. Okay, -5, that's a pretty ugly 5, because you get 3 minus 8 is -5, plus 1, I'm not even going to write the 1 down. What's the determinant of this one? Anybody? I heard someone in the background. 4, okay, because it's a 0 minus a -4, which is plus 4, times the 1 that we had there. So -2 times -5 is positive 10 plus 4 is equal to 14. Now, that leads me to want to ask another question. I don't think we've hit this yet. But if the determinant is 14, remember, in 2x2s, if the determinant was anything other than 0, then that matrix could be reduced. The matrix would have an inverse. Same thing holds here. That determinant is 14, therefore this matrix does have an inverse. We're not about to do what the inverse of that matrix is yet. We'll get to that later. But that's what this tells you. Since that's a non-zero determinant, this matrix does have an inverse. You're going to have to do some monkeying around with it to get that inverse, but that this matrix does have an inverse. All right, and that's what they got too. Good for them. And by the way, at the bottom of the page it's mentioned the theorem on the next page states that, and this is known as Laplace's expansion of a determinant after the French mathematician Pierre-Simon de Laplace. Okay, and you'll find Laplace's name all over physics and probably more math than physics, but you find them in physics as well. Did a lot of he progressed math pretty well in his times. He was one of the better mathematicians of his day. Okay, so here's theorem 3.1. Now I think you all have it, and it's a lot like the definition we just did, but I will all three of you have your books? Excuse me, wait a minute. I'm so sorry. I think we had a little rain shower here, and I think it dropped the temperature outside. Now the temperature dropped in here, and I'm getting a little chilly. I don't even have the ceiling fan on yet. So, now, theorem 3.1 says, okay, I was asking, do all three of you have your books? Yes, yes, yes. Okay, good. Here is theorem 3.1. Let A be a square matrix. You know it's got to be square, otherwise you can't take a determinant. So let A be a square matrix of order n by n. Got to be order n. Okay? Then the determinant of A is, and basically what we just had, except I'll have you note, now I've already erased the previous screen, now it's saying it's the summation of j equal 1 to n. That's exactly like we had in the definition before, but now, and this is what I was starting right before, aij, cij, okay, but you're letting j count from 1 to n. So those would be, the first one would be ai1, ci1, plus ai2, ci2, plus ai3, ci3, plus dot, 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 all the way up to ain plus cin. Notice the difference from this and the first definition we had that we started with today. First definition started on the first row. But guess what? You can use any row you want to. That's what this tells you. That's why they have an I there rather than a 1 for that first entry. Pick a row, any row, go down the row doing the element times its cofactor. Once you eliminate that row and column, and then plus the next one. Go down a row and determine the determinant that way. Or, and here's where the big or comes in, you could do the summation of I equal 1 to n, because it's an n by n matrix, of aij, cij, and that would be a1j times c1j plus a2j plus c2j plus a3j plus c times c2j, 3j, plus dot, 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 all the way up to anj times cnj. So guess what? You can pick any column you want to and go down that column and find the determinant that way. It doesn't have to be the first row. It doesn't have to be any row. It can be any row, any column. Okay? Now, just sort of to reinforce this isn't going to prove it, but it's going to reinforce it. I want to point something out to you. Just like we discovered here, if you can pick a row or a column that has a lot of zeros in it, your whole deal is going to be much easier. So guess what? We could have chosen the first column here, not the first row, and we could do the same thing. So let's do it. That zero entry is not going to give us anything. This entry here, the 3, what's the sign of the cofactor going to be for this 3? Minus. So that would be minus 3 times the minor for 3. So wipe out that row and that column and you get the matrix 2, 1, 0, 1. Okay? Okay, now we're going down the first column here. What's the sign for the cofactor of the 4 here? Plus, so that would be, I don't know what I just wrote there, but it's ugly. I think I wrote an equal sign, and I don't want an equal sign. I want a plus sign. Okay, let me get up here. I'm trying to get my pen to advance. There it goes, finally. Okay. 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 So that's going to be a plus 4 times the minor of 4. And that's a 2, 1, negative 1, 2. Does everybody see that? 2, 1. So the 2 didn't write. Ah! I did that. That was my error there. Okay. This still takes a long time to do this. Okay. 2, 1, negative 1, 2. That should be the determinant. Okay, so let's do it. This is a negative 3. Now, what do we have here? 2 plus 4 times the determinant here. 4 plus 1 is 5. And what does that give you? Negative 6 plus 20. Sure enough is equal to 14. Same thing. Okay, we could, if we wanted to, take the second column, do the same thing, or the third row and do the same thing. You could do the second row or the third column, yeah, but who would want to? That's more work. I'm lazy. I don't like to work that hard. And you'll get the determinant, same determinant of which one you choose. Choose the one with the most zeros in it. That's the key. All right. All right, for me to clear. Feel like a emergency room doctor. Clear? Okay, let's clear. Okay, there we go. Example 4. Oh my goodness. Example 4 is a 4 by 4. Okay. So let's do, here's matrix A. And this is a 1, negative 2, 3, 0. 1, negative 2, 3, 0. It's nearly as painful to write as it used to be. Negative 1, 1, 0, 2. Negative 1, 1, 0, 2. 0, 2, 0, 3. Slash some zeros and not others. And 3, 4, negative 2. Yuck, there it did it again. Something about holding it in place too long. Negative 4, 0, negative 2, or 3, 4, 0, negative 2. Now that 3 is out of line, but you see what's going on then. And those 2 zeros don't have slashes on them. I don't know why, I just was having trouble writing at the moment. So, okay. Now, how do you find the determinant? Okay. Determinant of A is going to be the determinant of this thing. And I think you can probably see some problems coming. Okay. What would you choose to do? You can choose any row, any column, and use that column or row to find out the determinant. Which one might you choose? I want you to be good and lazy about it now. James, you probably don't qualify here. What would you choose? Okay, no. A row or a column? Okay, row 1 has 1 0 in it, not a bad choice. Of course, row 2 has 1 0 in it. Row 4 has 1 0 in it. Column 1 has 1 0 in it, and column 4 has 1 0. So it's a good one, but no better than the others. However, row 3 has 2 zeros in it. Okay? But what better option do we have? Not 4. 3. Look at that. Column 3 has 3 zeros in it. I didn't slash that one, so maybe that threw you off and it got out of line. And now I can't get it to. This is such an aggravating thing. Okay. Slash those zeros. Oh, there it didn't slash well. But column 3, that's the one I would go for. Okay, if we're going to use column 3, we're going to go down column 3, right? So the first thing we're going to use is that entry. What is the sign of the cofactor of that entry, the 3? Anybody? Say again? Plus, you're right. So that's going to be 3 times the determinant that you have left over when you wipe out the first row and the third column. So that's going to be, let me wipe them out this time. Wipe out the first row and the third column. Okay, the determinant you have left is minus 1, 1, 2, 0, 2, 3. Everybody see what I'm doing? 3, 4, negative 2. That's all, folks, of your first step, because the other 3 entries here are all zeros. So you only have to deal with that first one. Okay? That's why we choose the row or column with the most zeros in it. It makes life simpler. But we still have a 3 by 3 matrix to go. Now I want to like crazy to show you a shortcut here, but they haven't done that yet. So let's go on and do the cofactors like we've been doing. What would be your next choice? You have 2 good choices here. What would they be? Anybody? You've got it. Either column 1, which has a 0 in it, or row 2, which has a 0 in it. So let's do that. So I think I'm going to come down here and do it. Don't forget your 3. It's still there. That 3 is multiplied by, now which you want to use, column 1 or row 2? I don't care. Not too much. I care a little bit. Column 1, that's what I like. Okay, so we're going to start with the first entry there. What's the sign of the cofactor of that first entry? The sign of the cofactor of the first entry. Positive, but it's a -1, so that stays a -1, times, if you wipe out that row and that column. Now, I can do that for you if you want me to, but it'll sort of mess up what we're doing later, but I can erase it easily. You want me to wipe it out physically or leave it? Leave it. Okay. So what you have left, if you wipe out the first row, first column, you have a simple matrix 2, 3, 4, -2. Does everybody see that? Okay. Now, we're going down the first column. That's what James said to do, right? So the next entry is a 0. Forget about it. That's going to be 0. So let's go to the third entry. What's the sign of its cofactor? Plus, so that's going to be a +3. And then we do the matrix that's left over when you wipe out the first row and the first column in the third row. And that's that matrix here. That would just be 1, 2, 2, 3. Does everybody see that? Yay or nay? All right. Yay! We got to get. Okay, good. Okay. Now, you have the 3. Don't forget it. You have now a -1 here. Let's not forget that either. But let's take the determinant of this 2 by 2. Those are easy. What is that? Okay. You got a -4. Okay. Okay. A -4. This is going uphill. Okay, -4 minus 12 is -16. Good. Like pulling teeth here. Okay. +3 times, and what do you have there? -1. All right. So that'll be a 3 times -1 times -16 is +16 minus 3, and 3 times 13 is 39. What does that tell you? That matrix we had there does have an inverse. Now, we haven't gotten there yet. I shouldn't be harping on that, but just reminding you, that's what it meant with the 2 by 2s. Also meant that here. Let's see how the book did. Oh my goodness, look at that. They got 39 also. Okay. Your smart move was to have started with that third column, because that had the most zeros in it. There it is. That was good to do. And I went on to wipe that out because we weren't going to use any of those anymore. Okay. Because then we're down to a 3 by 3. And then from there on, they were fairly easy to do. Another good move to either use the first column here or the second row. And they would be about equivalent. I usually go with the smaller numbers. And since -1 and 3, a little bit less than 2 and 3, I went with that. And James told me to anyway. So I have to do what James said. Okay. Does everybody see this? All right. They do all the cofactor stuff with the -1 raised to the even or odd powers and stuff like this. I found it so much easier just to, right off the bat, determine the sign of that cofactor, write it down. Okay? You can do that by plus, minus, plus, minus, plus. Remember? Now we get to show you a shortcut. Okay? Now, this shortcut, you remember, I'm getting my wires caught up here all sorts of different ways. Okay, a 2 by 2 is so easy you don't have to mess with cofactors at all. You really are doing them, but you don't have to even think about them. A 3 by 3 does have a shortcut too, that you don't have to worry about cofactors at all. So I'm going to take this one that we just did and show you another way to do it. Okay, I was just trying to move it here. So I'm going to come up here and find my eraser and erase everything here except that 3 by 3. I'll probably even leave the 3 in there just so you remember that's what we, oh, I didn't mean to do that. You remember it came out to 13. So let me erase everything else here. If you remembered my erasing on the old Fujitsu, it was a lot harder to do than this one. This one is a pretty broad eraser. I'd have to go back and forth, and it took forever for the numbers to disappear if you had too many on the old Fujitsu. So let's do this determinant. And actually, what I'm going to do, now this sounds bizarre, but it works. I'm going to erase the second bar. Okay? And here's what I'm going to do. Okay? Repeat the first 2 columns. 1, 0, 3, and 1, 2, 4. Okay? Now, here is the determinant of that. Now, that is not a square matrix, obviously, but all we've done is rewritten the first 2 columns. So the process we're going to do is going to find the determinant. So I'm probably shouldn't, but I go on and write it in as if we are doing a determinant. Though you know technically that can't be a determinant. But here's what you do. You take all your down diagonals. Remember, when you're going down, they're always positive whatever that number is. And what's the product of those down diagonals? One times 2 times negative 2. Someone answer. Negative 4. Okay, do your next down diagonal. Okay, that would be this one. What does that give you? Plus 9. Do the third down diagonal. And what does that give you? 0. All right, now, just because they're kind of in the way here, I'm going to take off my construction lines. I just did them so you'll see what numbers to multiply. Oops. Now it did it again with an eraser. Okay. Okay. Now, I'm going to do my up diagonals. Now, what sign do you reckon an up diagonal is going to be? No, no. Down diagonals are plus, up diagonals are negative. Okay? Remember, in our 2 by 2s, that's what we do. So this up diagonal is going to be a minus what? Minus 12. This up diagonal is going to be another minus 12. And this up diagonal is going to be a 0. Okay? What do we have here? Minus 24 minus 28 plus 9 is a minus 21. What did I do wrong? No, minus 19 I think it was, wasn't it? I can't even add. Minus 24, 30, no, okay. I thought for sure we came out with a minus 13, positive 13 before. Did I leave off? Well, I kept the same numbers. I couldn't have left much off. It was a 1, 2, wait. Oh, a minus 1. Oh, I know what happened when I lost the, remember, sorry folks, remember when I had accidentally wiped out this bar here, I also wiped out a minus sign. Let's start that one over. There, it did it again. Okay. I didn't realize that. That should be a minus 1 there. If you look in the book, when you wipe out the first row and the third column, you get a minus 1, 1, 2, 0, 2, 3, and a 3, 4, negative 2. Yeah. So that was a minus, and that would make this one a minus. I didn't realize I lost the minus sign there. Let's do that again then. Okay. So coming to down diagonal here, what do you get? Plus 4. Down this diagonal, right? And down this diagonal, yeah, okay. So now I'm going to go back and erase, and hope I don't erase too much here. Erase that diagonal, that diagonal, that diagonal. And now we'll go back and draw our up diagonals. Okay. And this would be a minus 12. This would be a minus a minus 12. See that minus 1 there? Yes, that would have been a plus 12. And then the last one would be a 0. So these two add to 0, and this gives you 13. And that's what we had before. Okay. Whew. I was being clever and not clever enough. Okay. They illustrate this at the top of page 114, and then they move on to example 5. Okay. Now, before they did example 5, they showed why this works. Okay. I don't know if I want to actually go through that or not, but remember, yeah, I think I will at least talk through it a little bit. Okay. So, and hopefully this won't be too painful to talk through. Okay. Okay. Now, let's sort of forget these last two columns here for now, but I'm going to come back and reuse them later. Okay, just sort of pretend those aren't there and you had just this matrix. Okay, if you were doing what we did before, we did this entry times these two, so there's A11, A22, A33 as you go down this way, right? Minus A11, A32, A23, right? But remember, that's exactly what you get when you go up this diagonal here. A minus, because you're going up, A11, A3. So you see that gives you the same thing. Okay. Then we did this entry here, A33 times A12 times A23. 23. A31, A12, A23. Okay, that was a plus times that. But if you look at this, that's this entry right here, this diagonal here. A2, A12, A2, 3, A1, 3, 1. That's that entry. So every one that we did before, we are doing this way. Oh, and then the last one was A33 times A23. No. Yeah. Okay. A31 and then minus A22, A13. Okay, a minus A, this one times that one times that one. Well, sure enough, that's exactly what, no, I'm sorry. This one times that one times this one. No. I can't get my pen to move. There it goes. Minus this one times that one times that one. And sure enough, no. This one times this one times this one. And that's exactly, I said it right the first time. That's exactly what you get here, minus that up diagonal. And there we have it. That's how we did them. It gives us the same results, and that's why it gives you the same results, because your pluses and minuses work out perfectly. Okay. That was supposed to be an explanation. It probably was more confusing than it was. Example 5 not only is in your book, you can go to larsonlinearalgebra.com for an interactive version of this type of an example. And let me clear the screen now. There we go. Okay. And here is matrix A. It's a 0, 2, 1. 3, -1, 2, 4, -4, 1. Okay, it says my internet connection is unstable. Were y'all able to hear me through that? Or did I break up? Can you hear me now? It did, okay. That's why. Okay, that 3, 2 entry there is a -4. It's ugly, but it's there. Okay, let's do the determinant by the means we just did. So the determinant here will be the determinant here. What I'm going to do is wipe out the brackets and okay. So I'm going to wipe out this bracket here and this bracket here, and then I'm going to expand. So you tell me what to write here. Zero, 3, 4. Repeat the next row, column, 2, -1, -4. Okay, now I'm going to put the bar here. That's not really a determinant bar, but it reminds me that's what I'm doing here. Okay, so you tell me what the determinant of that would be. What's your first entry? Anybody? 0. Next entry. 16. Last entry. Last down entry. -12. Okay, now just for my purposes, because it gets ugly really fast, I'm going to try to take out that line. Oh, I took out too much. I took out way too much. This is what I don't like about this eraser. It is too broad of a brush. Okay, let me fill that back in. That was a 0, 2, so that was a 2 there. And then the next was a 1 and a 2. Okay, do I have everything correct now? I think I do. Okay. So we did the down diagonals, which was the positive ones. Now let's do the up diagonals. What does that give you? Anybody? Plus 4. How about this up diagonal? Plus 0. And then this one? Minus 6. Perfect. Okay, let's add our positives together. That looks like a 20 to me. And our negatives together, that would be a minus 18. And that gives you a determinant of 2. Which means this matrix should have an inverse. Okay, now we haven't gotten there yet, but we'll get there. Okay, now there is a nice little illustration at the bottom of page 114 on linear algebra applied. Recall that a tetrahedron is a polyhedron. Poly means many, hedron means sides or faces. Okay, so a tetrahedron would be four-sided or four-faced figure. It has a triangle at the bottom and then triangle on each of the four sides coming up from those three sides at the bottom. Okay, four triangular faces. One practical application for the determinants is finding the volume of a tetrahedron in a coordinate plane if the vertices of the tetrahedron are x1, y1, z1, x2, y2, z2, x3, y3, z3, and x4, y4, z4. Okay? And then they tell you how to do that, and it says you'll study this and other applications of the determinants in section 3.4. So why don't we wait until section 3.4 and do that? Okay? So I don't know why they put that in now. In just a few sections from now, we'll actually do that. Okay, so let's move on to triangular matrices. Haven't we hit these before? Earlier we called them upper and lower triangular matrices. That's exactly what we're talking about here. When they say triangular matrices, it's either going to be an upper triangular matrix where you have the it has to be a square matrix. You have the diagonal has elements in it, and then all the elements above that diagonal, some of them at least are non-zero, but all the ones below that diagonal are 0. A lower triangular matrix would be the diagonal has entries, whatever it has, and it has entries below that, which some of them have to be non-zero, but all the ones above that diagonal would be 0. Those are your two types of triangular matrices. Okay? Now, if you have a matrix that's both upper and lower triangle, that means you have a diagonal matrix and zeros above it and zeros below it. Okay? Now, that's called a diagonal matrix. It is an upper and a lower triangular matrix at the same time. That means the only entries in it are on the diagonal. Only non-zero entries are on the diagonal. Okay, now, what if we were finding the determinant of So let's take your upper triangular matrix they give you next. I won't even bother to erase what we've got now. This is going to be pretty easy to do. This is a different matrix A, and we're taking the determinant of it, and this is the determinant, and the equal sign just doesn't like to go there. Okay, here is the matrix. Now I'm going to put the brackets in first, but then I'll put, okay, it's a 2, a 3, and a -1. Okay, a 0, a -1, and a 2, and a 0, 0, 3. Okay, there's your matrix, and we're going to try to take a determinant of it. Okay, and my question to you, what would be your choice of a row or a column to do? Okay, he chose row 3. We'll go with that, even though I wouldn't have chosen that one, but it's perfectly fine, a perfectly good one. So we're going to use row 3. And why did he choose row 3, by the way? You could have chosen column 1. I would have done that, but it doesn't matter. We're going to use row 3 because that's what you said first. Now, what do you do with that? Why did you choose it? Because it had the most zeros in it. It and column 1 both had 2 zeros. So if you're going to choose that, what is the sign of the 3 that you have down here? The cofactor of that 3. Sign of the cofactor for that 3. This one here. Second plus, you're absolutely right. And we'll write down the 3. And then we'll wipe out that row and column. I already wiped out the row. We'll wipe out the column. And then you do the determinant here. And that determinant would be 2, 3, 0, -1. That's the minor. Okay? And what's its determinant? -2. How did you get that? Okay. Well, let's see what you just did. You said a 3 times a 2 times a -1, didn't you? Those are just the product of your diagonal. Because you see, these 2 zeros here wiped out anything that they would have to do, and this 0 that you had left here wiped out that, so the only thing that you really used were your 3 diagonal elements. So guess what? The determinant of any triangular matrix is the product of the diagonal elements. Done. That's it. That's all, folks. Okay? Whether it's upper triangular or lower triangular, it both works. Or whether it's a diagonal matrix where zeros are above and below, of course, it's just going to be the product of those diagonal elements. So that leads, and this, by the way, is 3 times the -2 is -6, and that's what they got in the book as well. Okay, so here's theorem 3.2, which illustrates what we just said. If A is a triangular matrix of order n, of course, to be triangular matrix, it's got to be square, okay, of order n, then its determinant is the product of the entries of the main diagonal. That's all, the entries of the main diagonal, okay? Now, they show a proof here using mathematical induction, which is a pretty powerful little tool, and I sort of hate we don't have time to do it because it is something I'm hoping you may have run into it sometime in the past, but you may not have. I'm guessing you probably didn't. It is a very powerful tool for doing proofs. So you can go to the back of your book and in the appendix to see a discussion for mathematical induction. All right. So let's do example 6. Now this one I think I will clear. I'm learning to use this a little bit more easily. the determinant of a lower triangular matrix. Here is matrix A. Okay. Two, zero, zero, zero. This goes so much faster than my right finger did. 4, negative 2, 0, 0. 4, negative 2, 0, 0. Now, I don't know, can y'all see that control? Well, now it disappeared. Okay. Negative 5. I say negative 5 and write a 6. There's something wrong with the old gray cells. Okay. Okay. Negative 5, 6. That's the 6 I had. 1 and 0. And the last row is 1, 5, 3, 3. So if I ever ask you which you'd rather do, find the determinant of a 3 by 3 or a 4 by 4, what would you normally say? 3 by 3. But if you're ever asked that question, then turn around and say, what kind of matrix is the 4 by 4? Is it triangular? Because if it's triangular, it's easier than a non-triangular 3 by 3. Okay, so what is the determinant of A? Okay, hey. What did we just learn? Yeah, just multiply them together. What do you get? Negative 12. You like to work too hard. Okay, sorry about that. Okay, you could have done what you suggested, but so much easier. If it's a triangular matrix, this happened to be a lower triangular matrix, doesn't matter which kind it is, the determinant is just the product of those diagonal elements. And guess what, team? That finished 3.1. Okay, homework exercises here in 3.1 would include any of the odds 1 through 11, either 13 or 15, 17, and by the way, they're all at calcchat.com. Okay, they're also in the back of the book, just the answers are. Any of the odds 19 to 31, a whole passel of those, but even that big old number 32, can anyone tell me the answer to that one? That's a 5 by 5. That sounds like that would take an awful long time to do. 32. It's not a homework problem, so just look at it quickly. Tell me what the determinant is. Which row or column would you use? Nobody has his book open. Oh, okay. Well, what you would do if you have your book in front of you, pick the 4th row. That's all zeros. Guess what the determinant of that is going to be? 0. Okay. All right. Then do 33, either 35 or 37. They say you might need graphing utility on 37. They're all at Calc Chat, by the way. Either 39 or 41. 43 is a true false, but it has 3 pieces to it, so try to do that. Either 45 or 47. They're all both at Calc. Sorry, both at Calc Chat. Either 49 or 51. They're both at Calc Chat. 53 should be at Calc Chat. Any of the odds 55 to 61 should be at Calc Chat. Any of the odds 63 to 69 should be, I'm sorry, to 67 should be at Calc Chat. 69 should also be at Calc Chat. All right. Now, let's move on to 3.2. How are we doing on time? Oh, 12:14. We got an hour to go. Okay. I'm losing my voice, so hold on just a moment. Let me get a little something to drink. A little bit of carbonation sometimes help. I'm not sure that one's going to help any now. Now, I want someone to remind me of what our elementary row operations are. We've hit them several times. What are the elementary row operations? Oh, I think we did them in chapter 1. I'm sure we did them in chapter 2. What are your elementary row operations? Swap any two rows, that's one. That's another one. Yeah, but that's one you use most of any. It's adding a multiple of one row to another row, right? Okay, now, the question at the top of the first entry on 118 is this one. Here's a matrix. I go to right on the screen. Here's a matrix A. And we're going to be trying to do the determinant of this matrix. And they're asking which one is easier to do. Okay? A 1, -2, a 3, and a 1, a 4, whoa, that's ugly, a -6, a 3 and a 2, a -2, yuck. Now that was mostly my fault because I did let the pen touch the screen. I'm going to see if I can get rid of that too, but it doesn't look like I can. Nope. Okay. Alright. That first one was a 4. And this was a -2. 4, -9, -3. And the last row, a 3, a -6, a 9, and a 2. Okay. So that or B, find the determinant of B. Just tell me which one of these you think would be easier to do. And B is 1, -2, 3, 1. Same first row that we had before. And for some reason now the pen is not writing. Okay. This time the second row is 0, 2, -9, -1. Third row is 0, 0, -3, -1. And the fourth row is 0, 0, 0, -1. Okay, which of those two would be easier to find the determinant? Which one? Matrix B for sure, because that's an upper diagonal matrix, upper triangular matrix. Any triangular matrix, you just multiply the elements in the main diagonal, which would be 6. That determinant would be 6. I started to write it on the board. I can't write on the board. That determinant is 6. Just do the product of the down that main diagonal. 1 times 2 is 2, times -3 is -6, times -1 is +6. Okay. Actually, I would have done it +3 times +2 is +6. But yeah, however you want to do it. Okay. Now, here may be the surprising thing. I'm guessing the determinant of A is exactly the same thing. But guess what we've done? We've done row reduction using this 1 and wiped out those elements, made zeros there. Whatever this turned out being, we got it to be a 2 and wiped out these two. And whatever that turned out being, probably a -3, wiped out that one. And then by the time we did that, that was probably a -1. Now, that's just my guess. And I have taught the course before, so it's a pretty good guess. Okay? Now, let's do what they say there, but let's do it using, oh, what do they call it? Cofactor products, or whatever they call it. Okay? The method of cofactors, I guess it is. Expansion of cofactors, that's what they call it. I knew there's some name. Okay? And guess what? Hey, no zeros anywhere in that matrix A, so we're going to have to slug through it. So let's do that. Well, first it's going to be a 1, right? Because that is a plus position, right? 1 times this determinant. Tell me if I'm missing something. -6, 3, 2. And since I know how I'm going to do this, I'm going to repeat the -6 and the 3 because I'm going to expand that way. And then 4, -9, -3, and then repeat the 4 and -9. Because that's a 3 by 3, and that's how we're going to do it. Okay? And then we had a -6, a 9, and a 2. I hope I copied it right, and repeat the -6 and the 9. All right, now I'm going to put the bar there as if that's a determinant, but you know what I mean by that. Okay, then we're going to have, I'm using the first row, by the way, to do my expansion by cofactors. So I use the 1 here. Why won't it move? There it goes. Okay, I used the 1 and did this matrix down here. Okay, and then I'm going to use the -2, but that, ew, the cofactor sign of this position is a minus, so the minus times a minus is going to be a +2. Okay, and then I'll do the determinant that's left over. Now this time I think I'm going to wipe out my rows and columns because it's hard to see without it. Okay, and then this would be a 4, 3, 2, 4, 3. I'm going on and expanding it. A -2, -9, -3, -2, -9, and then a 3, 9, 2, 3, 9. Okay, I'm going to put a bar there as if that really is. Okay, now this is why I hesitated to do what I did. I'm going to need to now erase this one here. But it won't erase. Why won't it erase? Erase there. And now it won't. This is so aggravating. I don't know why it is. And I bet you there's a button I can push to make it erase, but I haven't found that button yet. There we go. I got that one done. Okay, so let's go back to my draw screen. And this time I'm doing the 3. Okay. Now first, what's the sign of this position? The cofactor sign of that position? Plus, minus, plus. So that's a plus, and it's a 3, so it's going to be a +3. Then we do the determinant of what's left. I'll try to write it in here. Let's say 4, -6, 2, 4, -6, because I'm setting this up to do it. -2, 4, -3, -2, 4. And then finally a 3, -6, 2, 3, -6. Okay, one last one. Now I've got to go back up here and get my eraser to activate again. Okay, let's see if I can get this one to erase this time. There, it did. Okay, and then with my drawstring here, I'll wipe out the last one. Now, I can't read. Was that a, yeah, that was a 1. Okay. What's the sign of that last element there? The sign, say again? -1. So now we have a -1 times the determinant that we have left over there, and I think I can read that one. A 4, -6, 3, 4, -6. I'm just repeating those. Okay. A -2, 4, -9, -2, 4. And a 3, -6, 9, 3, -6. Oh my goodness gracious. All right. So this is going to be a 1 times. Okay. Let's start doing, the reason I wrote those extra ones so I could do this. Oh boy, I'm hating this, aren't you? You know, now that I think about it, I believe you're right. Okay. But you know what? They wanted us to do this, those stinking people. Okay. So let's do it just for the practice of doing it. But you're absolutely right. B is definitely easier. Product of those diagonals. How are we doing on time? We're almost going to use our time up, aren't we? But this doesn't get too bad from now on. Well, the numbers are bad. Okay. But this is going to illustrate how much easier B is. Okay. If you do that down diagonal there, that's a 54 times 2 is 108. Am I right? I'm hating this too. Okay. Next down diagonal here is a positive 18 times 3, which is going to be a plus. And 18 times 3 is 54 maybe? Okay, you're much quicker than I am. And then the last one here is going to be a 36 times 2 is a 72. I'm hating these numbers. Okay. Now we're going to do our up diagonals, but I think in order to do them rightly, it would help to wipe out these down diagonals because they are, interfering. Okay. Okay, I've got to get my draw pen back. Okay. It was just a positive 3, was it? Yeah, it was. Okay, I didn't wipe out any other signs. Actually, I don't know. Okay. What's that again? Is it? Okay, good. Thank you. All right. Now we got to do our up diagonals. And this will be a minus 108, isn't it? All right. That's sort of good news because we have a plus one. This one, though, is going to be a all right. It's going to be a plus because it's up diagonal, right? Okay. 162, is that what you said? Okay, I didn't check it with you, but let's see. 54, right? Times 3. The 2's right. Yeah, I think you're right. And then the final up diagonal here is a minus 24. Okay. You know, I'm about ready to quit this one anyway, because they just skip a bunch of steps anyway. But just to show you, and this is just the first of 3 of these we got to do. Well, first, these and these go out. They add to 0. Now let's add the rest of them. 162 and 54 would be 216. And then add to that 72 is 288, I think. Okay, so 288. So that's going to be a 288. Now, they got a negative 60, which aggravates the fool out of me. We must have done something wrong. That 162 is a little suspect here. And did I lose a sign somewhere? I don't think so. Yes, maybe I did. What's that? I think this is a minus 3 here, isn't it? Yeah, I think it is. But anyway, you see the problem with trying to do a big matrix like this, especially by hand. By computer would be far easier. Okay? I think that's where it is. I think following the 4 in the second row, 4, negative 9, that should be a minus 3. I think that should be the minus 3 right there. And I blew it. Okay? And I'm not about to go and do it. Okay. Enough of that. The answer comes out being 6. Okay? They skipped all kinds of steps there and pretended they did them all, and you know they didn't. Okay? And it came up 6. All right. Now, how did we get from matrix A to matrix B? I've already given it away, I think, by saying we did row reduction, but guess what? We only did row reduction with adding a multiple of one row to another row. Okay? And here's why I claim that. Okay? So I'm going to go here and clear the screen, and let's do what they want us to do in example 1. Matrix B, this is a different matrix B here, is obtained from A by interchanging the rows of A. So here's, if I can, there it is. Here's matrix A. This is a different matrix A, a much easier matrix A. This is 2, negative 3 by 1, 4. 1, 4. Okay? Can anyone do that determinant for me fairly quickly? Anybody? Anybody? I've lost you all, huh? Did my internet go out and you can't hear me? Seriously, are y'all still there? I see James. Yeah. Okay, can you say something? Okay, good. All right. Did I get it right? 8 plus 3 is 11. Okay. Now, Matrix B over here that we're going to take a determinant of. How we get the matrix B is just swapping the two rows. That's going to be a 1, 4 and a 2, negative 3. Okay, and someone do that determinant and see what you get. Got it. Minus 8, yeah. Minus 11. Okay, now all you did was an elementary row operation of exchanging two rows, but that negated your determinant. It's a perfectly legal thing to do in row reduction, exactly like it said, but with determinants, it made the determinant change sign. Okay? Now, going to do a slightly different row, matrix A. Here's matrix A. That's going to be the determinant of 1, negative 3, 2, and negative 4. Okay, can someone do that for me fairly quickly? Anybody? Okay, again, I can't hear anybody. I hope you're still there. Okay, we do yes. Okay, minus 4 plus 6 is positive 2. Okay, now matrix B, we're going to do an elementary row operation to it first. And what that elementary row operation is going to be is using the 1 here and getting a 0 there. So what we'll do, negative 2 times row 1 plus row 2. What would that give us? We're using row 1, so write it down, 1, negative 3, and do that elementary row operation. Zero, 2, perfect. Okay, now let's do the determinant of that matrix. 2, hey, doing that elementary row operation, adding a multiple of one row to another row did not change the determinant at all. Exchanging two rows negated it. Doing the elementary row operation of adding a multiple of one row to another row did change the determinant. Okay, let's do another matrix A. This matrix A is 2, negative 8, negative 2, 9. And what's the determinant of that one? Nope. No, wait. I messed it up. Sorry. Okay, let's try that again. I was going too fast. 18 is 2. Okay. Now, the next B here, we're going to use the row operation we haven't used yet, and that is dividing row 1 by 2, which is legal, right? That would make it a 1, negative 9, negative 2, 9. What would that determinant be then? I don't know how I got negative 9. It's negative 4. Beats me. Yeah, you need to learn your division tables again, James. Okay. All right, what do we get here? Okay. What did dividing one row by a number do to your determinant? Well, actually, it divided it by that same number, 2. You divided by 2 before you got your determinant was also divided by 2. Okay. All right. We got about 30 minutes. Okay. Now, the summary of what we just did is on top of page 119, theorem 3.3. Let A and B be square matrices. They got to be square matrices. And by the way, they need to be the same size too. Okay? When B is obtained from A by interchanging the two rows, any two rows in A, the determinant of B will then be the opposite of the determinant of A. Okay? If the only difference is you've exchanged two rows, then that negates the determinant. Okay? The opposite. Now, when B is obtained from A by adding a multiple of a row of A to another multiple a multiple of a row of A to another row of A, the determinant does not change. That's why I said that A that we did at the beginning, that big old ugly nasty 4x4, I said I thought they used that process over and over again. We'll see. Okay? Because it doesn't change the determinant at all. And then finally, when B is obtained from A by multiplying a row of A by a non-zero constant C, then the determinant of B is going to be that same non-zero constant C times the determinant of A. Okay? And they do a little proof here. And then over on the left-hand side, and you can go through the proof, and it's probably not that bad to do, but I wanted to point out the guy on the left margin of page, I'm so sorry, 119. What it is, I think I'm getting very hungry, and I'm just losing blood sugar here. Okay, Augustin Louis, and I don't know how you pronounce his last name. I've read math my whole life, and I don't know how you pronounce it. I don't know if it's Cauchy, I don't know how to say it. I'm guessing it's Cauchy. That's how I usually pronounce it, but I have no clue of whether I'm right or not. Now, he's awfully young looking here, and the reason I mentioned that, his name shows up all over in math. He did quite a bit. Another really good French mathematician. Probably was along about the same time that, who was that last one we looked at? Laplace, I believe it was. Okay? Go back and see if I can find Laplace here, just to compare the dates. Because you see, France had sort of a golden age when just about everything they did in the math and science and everything, even the arts and everything, turned out really positive. And I can't find it, so anyway, I won't mess with it. But I'm guessing they were both in that golden age. Now, the interesting thing here is interesting to note that Cauchy's, I think is how you say it, his work on determinants, now this I found so interesting, preceded what Cayley's did in developing matrices. So what he was taking the determinant of, if he wasn't taking the determinant of a matrix, because they hadn't even come up with matrices yet. But he noted the characteristics there. So anyway, that's why it's mentioned here. A brilliant mathematician, young looking as he is here. I don't know if this is just a young portrait of him or if he indeed died young. Well, let's see, when did he die? He was 68, so yeah, that's a young picture. Okay, he didn't look that way at 68, I don't think. All right. So let's do example 2. and they say find the determinant of this matrix. I think I'm going to have to clear the screen. Okay, and here's matrix A. Zero, negative 7, 14. Okay, 1, 2, negative 2. And 0, 3, negative 8. Okay, so let's find the determinant of it. Now, anyone want to make an observation here? Okay, you certainly can, and that's a good idea. But what I would say first is this is not hard to take a determinant the old way, because all you'd have to do is use the first column. And that would be, I'm just going to do it quickly because it is doable. But then we're going to do what you suggested. And what is this? That would be this 1. And what's the sign of that 1? The sign of the position for 1? That's a minus. So it would be a minus 1 times the determinant that's left there, which would be a minus 7, 14, 3, negative 8. And that would be, this would be a 56 minus 52, I think it is, isn't it? 42. 56 minus 42 is 14 times minus 1 would be minus 14. Okay. Yeah, okay. Now, let's do what you suggested. Okay. Now, this would be, and we're finding the determinant now, so let's just do the determinant, because they didn't say anything else. They said find the determinant of this matrix. So we're doing the determinant of that, which is also the determinant of this, okay? And that will be minus the determinant when you swap those two rows. That's going to be a 1, 2, minus 2, a 0, negative 7, 14, and a 0, 3, negative 8. Agreed? From the rules we just did. What's the next thing you would want to do? Absolutely. And how would you do that? Okay, so that means you're also going to multiply the determinant by that. But we already have the minus, so it'll be 1/7 the determinant of 1, 2, negative 2, 0. Oh, did you say multiply by negative 1/7 or positive 1/7? Okay, so then the minus will then make that a plus. Okay, and then that would be a 1 and a minus 2. Agreed? That'll go away in a minute. Okay. And then we'll just write down the third row. 0, 3, negative 8. Okay. Now, what's the next thing you would do? Okay. Wait, okay. All we want is a triangular matrix. Don't worry about a complete row reduction. Reduce row, yeah. Okay. My pen decided to do strange things again. Negative 3, it's still doing it. What is wrong with it? Negative 3 times row 2 plus row 3. it just won't do it. Look at that. Every time. Okay. I have to write bigger, it seems like. Okay. Now, let's do that. Sorry, it's gotten in the way. Top row is going to stay the same. 1, 2, -2. Second row stays the same. 0, 1, 2. Or is that a -2? I'm pretty sure that's a -2, isn't it? Is it? Because it, yeah. Okay. And then this row now becomes 0, 0, -2. I did something backwards here. Okay. That's not a, okay. I did it backwards. Rather than, you divided the first one by 1/7, but that means you divided its going the other way. That's the same as multiplying. So this is multiplied by -7, -7/1. I can't get there. Okay, that is supposed to be just a 7. And it won't erase. I don't know why. And now it does that weird thing. Okay. And this is multiplied by 7. Okay. We're going to go back and explain that in a minute. Okay. So, what is your determinant of a triangular matrix? Anyone remember? Determinant of, say again? Yes, the product of the diagonal elements. And what does that give you? And this is, no, 7 times -2 is, yeah, -14. And that's exactly what we got. Okay. Now, where I botched up here, since, okay, let's go back and read again. When B is obtained from A by multiplying a row of A by a non-zero constant C, then the determinant of B is C times the determinant of A. Okay? And basically what it means, this is our determinant A, and when you multiply this by 7, you have to multiply the determinant of this by 7 to get that one. So it's, when you're going the opposite direction, they reverse the B and the C on us basically. So that is multiplied by 7. Guess what? Most of the time we don't use that one, but when you do, use it with very much care. Most of the time we only use the one that doesn't change anything, adding a multiple of one row to another row. And if we can stick with that, we are made in the shade. Okay? And we got -14 both ways. All right. Now, here comes something brand new. Okay? And it's so new, I want to warn you. Okay? I'm going to clear my drawings here. Here's how new it is. When you're dealing with determinants and determinants only, you're not trying to solve a matrix, you're not trying to solve a system of equations, you're not trying to do row reduction in any type of way whatsoever. If all you're dealing with is finding determinants, here is a key. Although Theorem 3.3, which was the one, elementary row operations and determinants, we just went over, okay, are stated in terms of elementary row operations, which only makes sense when you're doing Gauss-Jordan elimination, when you're doing anything else like that, solving systems of equation, you only do elementary row operations. But when you're dealing with matrices, and I mean not matrices, determinants, and only the determinant, the theorem remains valid when you exchange the word column with row. So now we have another tool. We can do elementary column operations. We can add a multiple of one column to another column. You can swap two columns, and you can multiply or divide a non-zero number by a column, existing column, and get a new column. And the effects of that will be the same as if you did it to a row. So now we can talk about column equivalent matrices, but you only do these when you're dealing only with determinants. Don't try to mix this up with your other operations we've done up till now. This is only strictly a determinant characteristic. Okay, now here's what we're getting at there. Okay, now here's a determinant. 2, 1, negative 3, 4, 0, 1, 0, 0, 2. All you're interested in is finding the determinant of that matrix. Okay? That's all you're interested in. Now, admittedly, this is not a hard determinant to do. Take the third row down there, okay, that has the most zeros in it. The 2 is in a positive position, so it's 2 times the determinant of a what's left up there, and that would be a negative 4, so that would be negative 8. I did it real quickly. I hope I did it right. That is negative 8. That wasn't hard to do, okay? But they say if you had had the insight to exchange, exchange these two columns here, this would have then said it's the negative determinant of 1, 0, 0, 2, 4, 0, and you see what that gave you? Negative 3, 1, 2, and that would have been minus the product of the diagonal, which is the 8, and that would have given you minus 8. And that was simpler to do. If you notice that just by exchanging the first two columns, you get a triangular matrix, those are so easy to do. Okay? These headphones are hurting my ears like crazy, but it's okay. All right? Let's do the next one there. Okay? This is the determinant of, and all we're interested in is the determinant. 2, 3, negative 5, 4, 1, 0, and negative 2, 4, 3, 4, negative 3. Now, I'm checking myself everything now because I've not at all sure made so many silly errors so far. Okay, now, just looking at that, that's not a particularly easy one, not bad. I would just take off that second bar and do reduction, expand it and do reduction the way you would do 3 by 3s. But they note that if you divide the first one by 2, which means it's sort of like you're factoring out a 2. And that's what we should have done on the last one. Factoring out a 2 of that first column, leaving you a 1, 2, minus 1, and then write the other 3 down, 3, 1, 4, and negative 5, 0, negative 3. Okay. Now, for some reason, they think that should be a lot easier to do. And perhaps it is. Okay. I would still use the middle row and do your row reduction that way. I don't know if that's how they do it. They don't proceed. They don't even tell you what the determinant is. But this is a legal maneuver. And you see, that's why the last time we should have pulled out the 7, not a 1/7. I was sort of backwards in my thinking there. Okay, it's sort of like you're factoring out that common factor. Okay, now let's do example 3. I keep using my finger to move things. I'll get used to doing this after a while. We got 14 minutes, so let's see if we can get the determinant of A here. Here is A, and that's the matrix negative 1, 2, 2, 3, negative 6, 4, and 5. Yuck! Why did it do that? 5, negative 10, negative 3. Okay. Now, we want to find the determinant of A. Okay. Now, there's a real tendency, because I'm just used to doing this, by saying, well, let's multiply 3 times row 1 and add it to row 2, add 5 times, multiply 5 times row 1, add it to row 3, you get zeros there. Okay? But much simpler had we done it this way. Okay? 2 times column 1, add it to column 2. So let's do that operation. If I can get my pen to come over here. Okay. 2 times column, that's supposed to be a C, 1 plus column 2. Okay. Okay. So that would be, oh, I didn't put my determinant bars here. I should have. I'm going to leave off the brackets now from now on. Okay. So we're using column 1, so we're going to keep it negative 1, 3, 5. Now, multiply column 1 by 2 and add it to column 2. 0. You do the next one. 0. You do the next one. What have we got here? So 2, 4, negative 3. It doesn't matter really what that is, because anytime you have a row or a column that's all 0, guess what the determinant is? 0. All right. Now, what does that tell you? This matrix is not invertible. Okay, now again, I'm saying that now. We haven't gotten to it in the book yet, but that is what we found out about 2 by 2s. I think the same thing will be true here. Okay. Now, there is a little blurb at the bottom of the page that I used to do a lot of. I haven't done much now for a long time, and that is Sudoku. Do any of you do that? No? It's a fun game. It really is. And I'll let you read that if you're interested. But guess what? They use matrices to come up with those puzzles. Guaranteed. Okay? They're arrays of numbers. My battery's going to go on my watch, but I still have time on my computer. It's 1:05. We've got 10 minutes. Let's see if we can do matrices and zero determinants. Top of page 121. Okay. Example 3 showed that when two columns of a matrix are scalar multiples of each other, same as two rows being scalar multiples of each other, the determinant of the matrix is 0. It's one of the 3 conditions that yield determinant of 0. If A is a square matrix, got to be square, and any one of the conditions below is true, then the determinant of A is 0. Number 1. An entire row or an entire column are all zeros. Obviously, that determinant is going to be 0. We've seen that before. We've seen it. We'll see it again. Second, 2 rows or columns are equal to each other. Okay, that will certainly work. And 1 row or column is a multiple of another row or column. There's another time when you're guaranteed the determinant to be 0. Is this all? No. These are just 3 that you can look at almost automatically and tell. Okay, so let's try to do example 4. Okay, I think we've got time. Here is matrix A. Okay, I think I'm going to clear this for now. Okay, go back here and do matrix A. Here's A is equal to good old 3 by 3. 1, 4, 1, 2, negative 1, 0, and 0, 18, 4. All right. Find that determinant. Okay, I hope I copied it right. It doesn't look very pretty, but I think it's right. Well, one thing is I don't have my closing bracket. Okay, now. All right. Does anything pop out at you right at the beginning? I don't see any 2 rows being multiples of each other, nor do I see any 2 columns being multiple of each other. Okay? But would a row reduction make a difference? Well, no. They're not doing any of that. They're just taking the determinant, which is fine. That won't be too bad. Now they're doing it by reduction by cofactors, or whatever you call that. What I'm going to do is just do my 3 by 3 thing, because I like that better. Now this does have 2 zeros in it, but they're not in a given row. So, all right, let's repeat the first 2 columns. 1, 2, 0, and 4, negative 1, 8, 18. The only thing messy about this is that big number 18 down there, but I think we can live with it. Let's see what happens. Let's do our down diagonal here, and what do we get? Negative 4. Do the next down diagonal, and what do we get? Okay, do the next down diagonal, and we get plus 36. Okay, now just because I'm used to doing it this way, I'm going to take out those three construction lines. Okay, go back and do our up diagonals. What's that first one give us? Second one gives us? Okay, and the third one gives us? 16 times 2 is minus 32, though, isn't it? Right? Because it's up diagonal. Okay, and what does this give us? 0. Minus 4 and minus 32 is minus 36 plus 36 is 0. Now, so like I said, you don't have to have multiples of a row or a column to be equal to 0. Now 2 by 2s, they're always going to be that way, okay? But this one's not a 2 by 2, and still you get a 0, okay? Now, what they did in doing theirs, I thought they just did row reduction. They didn't. I mean, let me get my eraser and undo this. Okay, I just looked at it real quickly and didn't look at it properly. I should have left that line there. Okay, I thought they were doing, well, what they did, I thought they were going to do, but then I didn't look at it carefully enough, and okay. Now what they did a row reduction here, and they did the first obvious one. They did minus 2 times row 1 plus row 2. Minus 2, there it does it again. Well, okay, that's ugly, but it's there. Okay, so what does this give us? And we can do the determinant here too, because that operation doesn't change a thing. So the top row stays the same, 1, 4, 1. That was right, wasn't it? Yeah. And then you get a 0, negative 9, negative 2. And then right down the third row, you get a 0, 18, 4. And what do you notice there? That's a multiple, so you can right off the bat say that's going to be 0. Okay, that was easier than the way I did it. But you had to have an awful lot of insight there to know that was going to happen. I really think they didn't have insight. They just said, well, let's do a simple row reduction and see what happens. Because to do the determinant of this one would have still been, this one would have still been easier than that, even if it hadn't come out that way, because you have the extra 0 there. So the bottom line here, if a simple row reduction, especially multiple of one row added to another row, is going to eliminate, make zeros like you have here, then that's an easy process to do, and then it's real easy to do that last step. So that's the bottom line. If you're only doing matrices, then do that elementary row or elementary column reduction. Okay, now we're down to 1 minute to go, and I don't think we're going to be able to do anything else. So we'll start next time at the top of page 122, somewhere there. And I don't think I have anything else written here. So that's going to be, well, no, that won't be it for today, because you were going to be screaming and yelling if I didn't give you some homework exercises. We almost finished 3.2, by the way. So I think you can do any of the odds 1 through 19. I think you can do either 21 or 23. And by the way, all these are at Calc Chat. They are in the back of the book, but also at Calc Chat. Any of the odds 25 to 35. There's a true-false 37 I think you can do. It's a Calc Chat. And we'll stop there and do the rest of them later. Okay? And that took us right to 115. Any questions, issues, concerns? All right. If not, let me, well, I can't do this on my Wacom, but I can here. Let me come down here and let's get out of that. Okay. Let's get out of that. Okay. I'm going to end the session unless any of you have any questions. Any questions? Oh, and by the way, I did put did I mention this before? I did put the test for chapter 2 out there. It's a PDF format. I think it's in pretty good shape, but if you have any problems with it, let me know. Okay? And that's going to be it for today. So I'll end the meeting and we'll see you on Thursday. Okay? Take care.